Hello, I'm Kevin Houston, and I want to talk to you about how to think like a mathematician. So as this is the first video on the channel, I thought I'd talk about something that's quite basic. What could be more basic in mathematics than the equality sign? So I'm going to talk about how you deal with that. In particular, how do you show that an equality is true? So equalities turn up all the time in mathematics. We've got sine squared x plus cosine squared x equals 1. We've got force equals mass times acceleration. E to the pi I equals minus 1. We've got equations such as ax squared plus bx plus c equals 0, and we know that the solution to that is x equals minus b plus or minus square root of b squared minus 4ac over 2a. And there are much more complicated equations than that. We've got the Navier-Stokes equations that you can see here, which if you understand the solutions to those, you could win $1 million. So if you wanted to show that an equality was true, what would you do? Well, let's say you had to prove that sine squared x plus cosine squared x equals 1 for all x. What's the most common method that students use? Well, I've often found that what they'll do is they'll take the equation and start rearranging it until they get something that's true and then go, aha, well that's true. So therefore the original equation must be true, right? So what they'll do is something like sine squared x plus cosine squared x equals 1. And then move something to the other side. And take that cosine squared over to the other side. And then maybe take square root of both sides, and so on. And sometimes this will lead them round in a circle. But even so, it's not a good method, right? So why is it not a good method? Well, let's try and prove that minus 1 equals 1, which is clearly not true, right? So, but let's use the method that we've just seen. So what I can do is I'll take my minus 1 equals 1, and it's an equation, so I can do something to both sides and it doesn't change anything. So I end up with squaring both sides. Okay, that's perfectly legitimate to do. And I end up with 1 equals 1. So we conclude, the original thing must have been true. Well, clearly it can't have been. And things go wrong because once you square, then you change things. And the problem is in assuming what you had to prove. Right, we should never assume what it is we have to prove. So assuming minus 1 equals 1 is where we went wrong. So it's not a good idea to start off with the equation you're trying to prove. So what should you do? How do you show an equality is true? Well, what I tell my students is start with the complicated side and do something with it. Right, and then during lectures, whenever we come across something where we have to show an equality, it might be in a theorem or something, I ask my students, okay, what do we do? How do we show inequality? And the idea is that they're supposed to say, well, we start with a complicated side and do something with it. Let's see this in action. Let's go back to the sine squared x plus cosine squared x equals 1, one of the most basic equalities in trigonometry. So what I'll do is say, well, what's the most complicated side? And in this case, it's kind of obvious, right? It's the thing on the left-hand side, the one involving the squares and all the sines and cosines. So let's take that. Sine squared x plus cosine squared x equals. And we have to do something with that. So what could we possibly do with that? I mean, if we're right at the start of trigonometry, there's not much we can do. But one of the things we can do is use the definition of sine and cosine, right? So the definition of sine is it's opposite over hypotenuse. And for cosine, it's adjacent over hypotenuse in a right angle triangle. So let's substitute that in. So we end up with opposite over hypotenuse squared plus adjacent over hypotenuse squared. Right, so I can then expand that out a bit. So I end up with o squared over h squared and add on a squared plus h squared. Well, it's an addition of fractions, so the common thing that you're told at school is to take a common denominator. Okay, so we get o squared plus a squared over h squared. And the opposite squared plus adjacent squared, well, that's equal to hypotenuse squared. Right? When we add those two things together, that's just Pythagoras' theorem. So we end up with h squared over h squared. And that's equal to 1. Okay, so you can see there we've got this lovely little long list of equations where every step is kind of straightforward, right? There's not much thinking to do, but we've now clearly proved that sine squared x plus cosine squared x equals 1. Right, let's see another example, slightly more complicated this time. cosec squared of x plus sec squared of x equals sec squared of x cosec squared of x for all, and then I've got a condition on my x there to try and avoid functions blowing up, right? Because some of these functions are not defined at certain values of x. Okay, here, which is the complicated side? And which is the side you could do something with, right? Okay, so you probably could go for either here, but I'll go for the left-hand side. So we've got the cosec squared x plus sec squared x equals, again, what can we do? Well, we could use the definitions. What are the definitions of cosec and sec? Well, cosec is 1 over sine and sec is 1 over cosine. So let's apply those. Okay, so we've got something involving sines and cosine squares. Then again, take common denominator, and we end up with, on the top, cosine squared x plus sine squared x, which we know is 1. So we could replace that with 1. Right, and a lot of these trigonometric identities, what you're actually trying to do is find out where you're going to use cosine squared x plus sine squared x, right, equals 1, that is, because that appears lots of times. So we get the equals 1 over cos squared x sine squared x. And we can pull those apart into the right-hand side, the sec squared x cosec squared x. Right, this method is a good method, but it's not always the best method. Let's look at this example here. Prove that 1 plus tan squared x equals sec squared x for all x not equal to, well, I mean, I'm just going to ignore that really, because that's just to avoid things where we get a bit of a blow up. It's not really important to our argument. Okay, I could take the complicated side, which perhaps looks like the 1 plus tan squared x, but actually I think in this case, the better way to prove it is to start off with sine squared x plus cosine squared x equals 1, and then divide through by cosine squared x. Because if we do that, we end up, because tan of x is sine x over cos x, we end up with tan squared x plus, well, cosine squared x over cosine squared x equals 1, and then we end up with 1 over cosec squared x, which, applying the definition of sec, we get sec squared. Okay, so I think that's an easier way of proving that particular identity. Okay, so sometimes it's not always the best way of doing it, but I think if you just don't know where to start, then I think just ploughing in with take one side, see where you go, I think is a really good method. And if you're really stuck, then just writing down the equation and trying to rearrange it can often give you ideas. So even that's not completely hopeless as a method. It's just that when you come to write it up, don't use the equation that you, don't assume the equation that you actually have to prove. Right, so that's basically how you show an equality is true. Start with the complicated side and do something with it. But actually, this works more generally. So it works for inequalities too. Let's say you have the inequality 2 to the power n minus 1 less than or equal to n factorial for n a natural number, where that n exclamation mark is n factorial, which means n times n minus 1 times n minus 2 and so on. So for this particular example, I'll actually do in a later video on induction. Okay, I'll leave that for you to think about until the actual video. Okay, so that's how you show an equality. Now, I've written a book, How to Think Like a Mathematician, which is jam-packed full of similar ideas. There's a link in the description. And so, until next time, bye.